So let's get started. So when we left off on Thursday, we were talking about tracing through distributed systems and causality. So last time we talked about consistent cuts, and I left you with the question of how can you actually build this? How can you actually implement this? And so today what we're going to do is talk about a technique that was introduced in 1985 that describes a way to do this. Now, the important thing to keep in mind as we talk about this is the technique we are discussing here doesn't give you a state that the system necessarily experienced. It simply gives you a state it could have experienced. So this is the complication in distributed systems. When you have lots of things that are not serialized relative to each other, it is difficult to determine the order in which things actually happened. So probably not very many of you know much about quantum mechanics, but much of quantum mechanics is about the same sort of thing. We don't actually know what's going on until we look at it. And literally in quantum mechanics, they have this easy principle, which is the moment you look at something, the moment you measure it, it collapses and you get a distinct response. But it doesn't tell you what the system looked like before or after. We don't even really quite have that much to go on here. What we do is we see a possible state that might have happened. But that's often enough for us to figure out what's actually happening. So we talked about global state. We talked about consistent cuts. We talked about inconsistent cuts. Inconsistent cuts are those where something in the cut happens before the event that caused it happens. So it's a causality question. A causes B. If I see B in my trace but I don't see A, I'm sitting here saying, what? How did this happen? How could I possibly be in this state? And so the answer is just don't consider those states because they're not valid states. So in Chandry-Lamport, the key insight was you can actually add these marker messages. The marker messages themselves then identify what our cut is. In essence, think of the marker message as being the way that we distinguish. When everybody has seen the marker and it goes back to the original, we know that we've captured something from all of the intermediate processes, all the intermediate nodes. So we have some assumptions here. We assume that all channels are first in, first out, in the order the message was arrived. So we don't have priority queues. We have more like what you see in a typical network, which is I have a channel, a message shows up in that channel, 10 messages show up in that channel, and I process them one at a time, first in, first out. Now, if the channel is full, I know that people have taken 317. What do you do when your buffer's full? You cry. Well, that's one option, but I tell you in the real world, you'd be crying an awful lot. It's a good answer, though. What else do you do? When you only have room to carry 10 things and you need to carry 11, what do? You drop one thing. Which one do you drop?
The one that came in last.
So he wants you to draw one that came in last. Anybody want to disagree? I like disagreement. It's where you learn things. Ever talk to an AI? Disagree with it. Tell it to disagree with you. That's even more interesting. Ever seen Family Feud? You know, like TV game show thing where they ask people questions and then they give the survey answers up on the top of the board. That's what it's like talking to Claude or ChatGPT or Grok or any of those. What they do is they give you the Family Feud answer. What's fun is when you go back and say, show me the answers I should be considering that aren't on your list. That's when things get real. So what can you do besides drop the last thing you received?
Drop the first thing you received.
Drop the first thing that you received. Why would you want to do that?
You want the most recent state.
You want the most recent state, which happens to be the last thing that came in. So maybe there are situations where you'll drop the last, sometimes you'll drop the first. Anybody want to argue about dropping things in the middle?
Maybe you don't want, you want to drop randomly, so you get like you get a little bit of everything.
You're sampling now. You're thinking of your queue as a sample of the things I'm going to look at, so I'm going to pull out of that queue and say, these are the, I just won't have time to look at these. I mean, when you're trying to prioritize what you do with your day, with your week, isn't that kind of what you do? You sample. You drop things in the middle. So there are times when you might want to choose any of those, but none of them violate the first in, first out principle. Because as long as you haven't processed it yet, you're okay. So you can drop things. That's the network allows that. The network assumes that you can drop things, and you can drop them from the beginning, the end, or the middle. There's really no way to tell the difference, and they all work. What we do assume is that channels are reliable. No loss, no duplication. That's a big simplification, isn't it? That's kind of what we do when we put TCP on there, because that's the purpose of TCP. Is TCP the only way to get this kind of no loss, no duplication guarantee? Three possibilities here. Yes, no, maybe. I'm getting the sense that people are sitting in the maybe camp. That's fine. Indeterminacy is the normal part of life. RPC is another way of doing this. TCP doesn't have to be the thing that you use. RPC is another way of doing this. Sometimes the things that you asked for don't matter because they've become stale, not stable. What time is it? You get the message tomorrow. You send me back the time when you get it, not when you received it. I don't want to run that over TCP, because what will TCP give me? Well, if it has to repeat it, it's going to send the same packet again. So we're going to get the time when it first answered, not the time now. The other assumption here is that the graph is strongly connected, which means that every node can talk to every other node. Now, we can actually deal with the cases where we relax these things, but let's start with the simple model first, because the simple model helps us understand the basics, and then we can say, now let's loosen this parameter and see what falls apart. It's kind of the way the real world actually functions. We don't have a global clock. We don't have the ability to freeze things. We just have these markers with this particular model. So the idea is that if you have processes P and Q that are exchanging messages, what you want to do is figure out where there's a consistent cut. So what you do is a process initiates a snapshot by recording its local state and then sending a marker out that asks everybody else to capture their local state. So then it starts watching the incoming messages on all the channels. And here's the interesting point. It's going to get reflections back of those markers. When it sees that reflection back of those markers, now it knows what the other node's state are. And when it knows that it's heard from everybody, it can stop. And remember, it's a fully connected graph, so we know we're going to hear back from everyone at some point. It gets much more interesting when pieces of it aren't fully connected, but let's keep to the simple case. So, when process Q receives a marker on a channel, if the first marker, if it's the first marker that Q has seen, it records its local state. It records channel C's state as empty. It basically says, I don't have anything that I haven't processed yet since the last marker. That's what the channel is the channel state is in this case. It sends a marker on all of its outgoing channels, the same marker. And then it starts recording all of the other incoming channels. If Q's already recorded something about its state, then what it's going to tell you is all of the messages that it has received since the snapshot before the next marker. So in essence, what you're doing is you're giving differential. You're saying, this is where I was last time. I didn't have anything to tell you about. Now I have something to tell you about. Here are the things that are inside of my window of change from the first marker to the second marker. And that's the response I'm going to send. Anybody see any challenges with this? I mean, from a conceptual model perspective, this is great. If you actually were trying to implement this, these messages could get very large very fast. I mean, it's not like networks run at 800 gigabits a second or anything. I don't know, I haven't looked recently. Does anyone know what the fastest network cards are now? Last I looked, they were 800 gigabits a second. How fast is 800 gigabits a second? It's probably faster than the internet you have at home. How about if we compare it to something else on the computer, and that is the speed at which the processor can speak to RAM? Anybody know what that number is? It's actually not that far off from there, probably between 100 and 200 gigabytes a second. So 100 gigabytes is 800 gigabits. So literally, network cards today speak at the speed of memory. And that is very different than when they were doing this in 1985. In 1985, what was the speed of a network? Anybody know? 10 megabits per second. And that was way slower than memory speeds. Networks were way slower than disks even. Disks really haven't gotten a lot faster. Maybe one order of magnitude. We've got lots of tricks we play with disks to make them look faster, but they're not a lot faster. So they've kind of stayed about the same. Memory has in fact increased, but networking, of the three big pieces in the computer architecture world, that's gone way, way out here. And the reason I mention this is because what we're talking about is why this no longer necessarily becomes practical to implement in production, even though it is a good conceptual model. So from a conceptual model, what do? Process, hey, here's a marker. I want to grab a global snapshot. Other processes get the marker, and they say, this is what I've seen since my last marker. And if I haven't seen, so if this is the first marker, I haven't seen anything since my last marker because I haven't ever seen a marker before. And now I start sending that, flooding the network with this, right? I'm literally sending this to everybody else. So as we start walking through this, we can see those marker messages come in. So the M's are our messages, the SQs are our marker messages, and they are capturing the state and sending it out to the other nodes. When the snapshot is complete, we know it's complete because, in fact, the processor that initiated the marker message has received a marker message back. It's received a reflection back from its original request. So now it knows that it has seen a flow of markers through the system. Now, maybe that helps you see why that would roughly correspond to a flow of messages through the systems. The markers are basically messages. They're just control messages as opposed to data messages. And since this was a flow of control messages through the system, they actually help us understand what could have happened to the data messages that went through the system. It doesn't mean we did. It means we could have. So why does this work? Okay, so since we have FIFO channels, the markers ensure that all the pre-snapshot messages arrive before the marker, all the post-snapshot messages arrive after the marker, and no message crosses the cut backwards. In other words, what we've done is defined a way of getting a consistent cut. Remember, consistent cuts were about causality, about making sure that we don't see an event now that hasn't happened in the visible past. I mean, seeing things that have If we see those in our cuts, then what we have is like magic, and we can't reason about that. So really all we're trying to do is ground ourselves. I think the hardest part about this conceptually is to think and say, but wait a minute, this doesn't actually represent a state of the system. And you're right. It just represents a potential state of the system that is enough, it's consistent enough for us to reason about. When you look at the DS Labs infrastructure, one of the things it actually does, it explores the state space. In essence, the different orders in which these messages could have arrived. But the problem with those kinds of state spaces, anybody know what happens in a state space like that, where you're trying to see all possible paths of messages in a network? Why don't we just capture everything? Why don't we test every single possible path through this large network? I mean, even 5 nodes, it's surprising how fast it grows.
There are exponential possibilities for that, so that's not feasible.
It's not even polynomially bound. Right? This is at least a power set. I mean, in 2 to the n, well, actually, it'd be the number of nodes into the m, I guess, where we have to pick some m. You're like, wow, how am I even going to keep this thing in memory? I mean, we struggle to keep order n cubed sized things in memory. What are we going to do with something that doesn't have a polynomial bound on it? All we have to do is prove that p equals np, and then we're done, right? Then, well, we'll be able to save that. Although p versus np is about computation, not about space. Our space representation here is what's blowing up. Anybody take 421? See, that's the opposite end of a systems class, right? That's the theory side. Space usage actually grows much slower than computational usage. It's interesting. All right, so the Chandry-Lamport algorithm doesn't capture a state that actually existed. It captures a consistent state, one that could have actually existed. So we may not necessarily know what went wrong, but at least we have an idea of what could go wrong. So I mentioned the state space explosion problem with DS Labs because it's using a state space explorer. And a lot of what we're trying to do when we start doing state space exploration is see if we can identify potential bugs. And this, I think, is really the hardest part about building distributed systems. The failures are very hard to diagnose because there's no clear ordering of events. Often what I'm doing when I'm looking at a failure is I'm basically building this kind of consistent cut model saying, this would explain what I saw. It doesn't prove that's what happened. But if I can see the bug, I can see the failure, I can fix that failure, and maybe it will fix the failure that actually occurred out in the field. Because these kinds of complicated situations don't arise when you're sitting there on your computer testing it. This is the challenge when you get to large-scale computing. There's no test system as large as what customers are actually using in deployment. When you talk to people at Amazon or Microsoft or Google or any of the other large cloud companies about these kinds of problems, they will literally tell you that what they end up doing is they end up testing in production. If you work for one of those companies on almost any of the products that are tested in production, you will probably end up with what is called pager duty. I'm not sure if they actually use physical pagers anymore, but we all carry these phones around which can act like physical pagers. And what happens is when something breaks down Someone has to step up and look at it and analyze it. And that's why these types of models are really important. Because if you want one of those jobs that pays you enough to be worth like being on 24/7 part of the time, you have to be able to reason about these, and you have to say, what could have caused this? And the pager thing, it's actually not just a myth. I actually have a friend who, in November, the day before Black Friday, I think it was in the US, and the US Thanksgiving, their order processing system stopped working properly. And so the messages started coming in at like 3 a.m. I mean, that's the hot seat, right? Literally. Finding out that you have to debug this thing in production just before the busiest time of the year. So you have customers who are yelling at you. So this is enough for us to detect deadlocks, premature termination, garbage collection events, because all we need is consistency. We don't necessarily require actuality. So the term reachable is used to indicate that we can get from one state to another state. So if we started here and we ended here and we recorded some intermediate state here, all we care about is that we could get from here to there. That means that this state, however we got to it, is reachable. It doesn't mean that's the only path. It just simply means there's at least one path. And I've mentioned lattices already. Lattices are an expansion of that idea of reachability. Now what we're talking about is creating an accumulation of all of those paths. So it's not just reachable, but it's now multiple potential paths through here. Why does that become important? Strong consistency tends to be expensive. It tends to be slow. And the thing we don't want as we start talking about large distributed systems is we don't want things to be slow. The limit that we're trying to work with is the propagation delay, the time it takes for messages to move through the network. It shouldn't be because of the protocol that we put on top of it in order to ensure consistency. Now, I'm not sure I've actually clearly defined what consistency means. Does anybody know what it means for a system to be consistent? I know you've been reading about databases because I torture you with those readings. And the goal of having you read those things isn't to understand databases at a level where you could turn around and build one. The goal is for you to understand the complexity of the data structures that are involved, because those data structures are what defines consistency. When you start balancing B trees, B plus trees, B star trees, the various different kinds of data structures that are involved there, you have the consistency problem of your nightmares. You know, you decide you're overflowing a leaf in a complex tree, and suddenly you have to break that into two, and then you find out that that means you have to break the one above it, and then we have to break the one above that, and the one you have to break above that, and pretty soon, you know, and I've actually seen this in the real world, you end up with breaking 11 levels of tree. How often does that happen? How often do you actually have to break a multi-level B tree or B plus tree all the way up to the root? I wasn't looking for an exact number here, even a scale. Maybe we should ask the guy who just came in.
Almost never.
That's the problem. How do you test something that happens almost never? About 5 years ago, there's this event. No, 6 years. My gosh, where does the time go? About 6 years ago, there was this event that happened roughly in this time period. I was actually working on a project in Cambridge at Microsoft Research about holographic storage. And the interesting thing about holographic storage was that when you read holographic storage, it degrades the image. Now, the physics behind that are holographic storage records an image inside of a substrate, usually some sort of very cheap kind of glass, actually. And then they record additional data at slightly different angles to the original data. The way you read it is that you project light through that. The way you write it is you project light through it at a much higher amplitude. So it's much brighter, basically. And so you read it with a much lower amplitude. But every time you read it, you create a certain amount of noise in the glass itself. I was there to model the performance of this particular substrate when you hit that threshold, when you hit the threshold that said time to read the contents of that region of the space and put it someplace else. And this turns out to be, the basic mechanism turns out to be fairly common. That's the way pretty much all storage devices work these days. They actually write in what are called zones. And a zone is write once, read many, and periodically you rewrite it. Now, most of the time, the reason we rewrite it is because since we can't write it easily, they're large, they're difficult to deal with. If there's lots of space, lots of data in them, it's not space, it's data. There's lots of data in them that represents space that we could reclaim because nobody's using it anymore. What we have to do is we have to read all of the data in and then get rid of the stuff we don't need. We have a much smaller block now. We write it someplace else, and then we update a mapping table that says this is where this logical data is actually physically being stored. All of the other media, though, don't experience enough what's called read wearing to justify that. But this particular one did. So this was a very interesting exploration of this space. And what I found as I started modeling this was you often had to run for simulation 5 years before you would even see one of these events that required that you read a block and write it someplace else. So now you get into the complex, edgy conditions where you're reading a block and you only have one block that's writable. And that can happen, even though you're only at 20% utilization. You could have lots of blocks that are just kind of partially used and all need to be cleaned up. So you then have to make sure that you have the resources necessary to recover from that particular state. These are the kinds of edge conditions that drive us crazy because in storage, if you're out of space, I can't just reboot the machine and make it all get better. It doesn't happen that way. This is persistent data. And persistent data you have to actually maintain in a consistent fashion. So you have to define, what does consistent mean? It depends upon the data. Databases have complex data structures, which hopefully you've started to notice as you've been reading about databases. They have complex data structures that often involve updating multiple different locations in the database. And it only gets worse as we add more functionality on the top of the database. We start with something simple like a key value store, and yes, we're dealing with blocks of storage, and we're dealing with the potential of having to walk up B+ trees and split them. And in order for you to define what consistency means in that model, you have to understand the model. I mean, I can give you an abstract state machine description. Presumably, you've studied state machines. You could basically say, I have a state machine model where there are a set of distinguished states that are called consistent. And for every inconsistent state, there is at least one transition from that inconsistent state back to a consistent state. I don't know if this will help anybody or not, but basically it says, something horrible happened here, go back here. Now, something horrible happened could often mean there was a power failure, or the operating system rebooted, or the underlying media threw an error. I don't know what all of those potential causes of failure are, but over time, as you run these things in production, what happens is your list of potential failures grows and grows and grows. Because the things that never happen when you're testing it actually happen in the real world. The function of a lattice is to realize or to admit that consistency can be achieved by walking through multiple paths. So if I have a set of states, let's say I have a state Si and another state Sj, and both of those are labeled as consistent, I can go through multiple other substates. But the point is, no matter how I get from Si to Sj, there has to be some path that gets me back to a consistent state. A lattice is just one way of recognizing this. What's cool about this particular model of consistency is it says the system can be inconsistent if you snapshot it, but all nodes will eventually reach a consistent state. And hence the name eventually consistent. You walk from wherever you came from to class here. How many different possible routes could you have taken? Could you have gone via Hong Kong? Probably not by walking. How many realistic routes? How many different ways? Do you take the same route every time? How many of you are creatures of habit and go exactly the same way every single time? There you go. Okay, so you found a route. Are there other routes potentially? Yeah. Right, and if you end up starting in a different state and you still need to end up here, do you go back to where you know the old route is and follow it, or do you simply adjust and find a different route?
Just adjust.
Right. So this is exactly what we're talking about, this kind of adjustment. For you, the consistent state, for whatever reason, is to end up here on Tuesdays and Thursdays at 11:30. We don't care about the intermediate states here. That's kind of what's interesting about lattices, is that for all intents and purposes, we can collapse all of those possible paths or all those possible routes into a common bucket, this lattice structure that says here are all of the possible ways through the network, through the messages of the system to get from one consistent state to another consistent state. So a property phi is stable. If once true, it stays true forever. So this is a durability consideration. Something is durable if once it has become true, it stays true. Piece of right one's memory. A deadlock is literally one of these states where once you're in a deadlock, you're dead. You're done. You're not going to make any further progress. How many of you have ever debugged a deadlock? Couple of hands. Well, kind of, sort of. I just rewrote all the code. Get rid of those locks, those pesky things that get in the way. Why do we use locks? It ties directly into what we were just talking about. What do locks give us? A timing mechanism. I've never thought of a lock as a timing mechanism. Interesting. How do you tell time with a lock?
Well, you know, anything that's accessing the resource while the lock is active has to access it after the lock gets unlocked. So the
Okay.
process has
So in fact, what are you really doing with the lock?
well,
What is the intent of the
the
lock?
intent
How's
of
that?
the lock is to prevent other things from accessing.
And what do we call that?
I forget the name.
I would call it consistency.
Yeah.
So locks are a way of achieving consistency. Now, in that particular case, they achieve consistency by enforcing a linear order. There's a linear order of events that happen, and that guarantees that we end up with consistency. What happens if we don't have locks? This is a really interesting question because it's going to get us to a conversation about this in I think 1 or 2 lectures, 2 lectures probably. How are locks implemented in computers right now? Instructions. So they're actually implemented by the hardware. I think that's kind of where I was going for. Can you implement locks in software? Turns out that you can, but it's much harder than people think. The academic literature is, I wouldn't quite say filled, but it has a number of instances where people propose software locking paradigms only to basically find out that the algorithm they suggested didn't work right. It's actually harder than you think it is. Now, when you don't have hardware, like, oh, I don't know, because you're operating over a network, you have to solve exactly this problem. So deadlocks often happen in local systems because we have a lock, some sort of resource manager that gets entangled with another lock, or that something goes wrong and we don't release the lock. But regardless, I need to do something. I try to acquire a lock. The lock is contended. Someone else owns the lock, so what do I have to do? I have to wait. And in real-world locking situations, we end up building things like, I need this lock, but I don't want to wait for it. I just want to get it if it's available right now. And if it's not available right now, I'm going to do something different. This is one way of actually building to break deadlocks. You say, oh, I'm holding this lock, and there's this other lock that I need, but I'm supposed to have acquired that other lock first. And I don't want to drop my lock if that lock can just be acquired without contention. And it turns out there's nobody's waiting for that lock, and we can just give it to you. We can do that. It doesn't violate any causality, and it works. And it's way more efficient because most of the time those locks aren't contended, and you avoid the deadlock. But if you don't do that, if you just simply say, grab lock A, then lock B, and you say, grab lock B, and then lock A, there you go. That's kind of the classic two-threaded deadlock scenario. But we're going to do this in the network, and we're not going to use locks. That's kind of what the point of distributed systems becomes. One of the other reasons I torture you with those database readings is because the distributed systems community and the database community share common roots. The problem of distributed systems arose because once we had databases, people said, how do we keep multiple copies of these databases in sync? And that's what gives rise to distributed systems. These issues around consistency. What does consistency mean when I have 2 replicas of a database? Well, it kind of means they're replicas. They need to be the same. So we can define consistency at a very high level there by just simply saying they're identical. But how do you do that? How do you make them identical at the same time. Because you don't want them to be identical staggered in time, although I just talked about lattices and the fact that sometimes you can get away with that. But in a database, what we typically want is we want identical at the same time. What happens when we go from 2 to 3? Why would you want 3 copies of a database? Think about it. We'll come back to it. We say that once a process becomes idle, it stays idle, so we have a termination property that is stable. We have an object X is unreachable. Nobody's using this blob of memory, I can garbage collect it. That's a stable property. And these stable properties are going to be useful for us as we start analyzing our systems. And then, of course, all crew are assigned, that Southwest debacle that I talked about before. These are the kinds of things we think about. These stable properties become invariants of the system. They are the things that we say, this must be true. And then we can reason about the system based upon those invariants. So the stable property theorem actually says if phi is stable and phi holds a snapshot of S star, then phi holds the actual current state. So in other words, we're looking at our lattice. We see that one of these states, the S star state, the one we went through, I see what we're doing here, okay, is a state that we actually went through. We actually that we know what the state of the system was at that point in time. And this is going to be really important because we are going to actually demonstrate a limitation that shapes the way that we build distributed systems, what's called FLP, Floyd Lynch Patterson. Okay, so I'm not going to go through the proof in formal detail here. I'm just going to try and make sure that this makes sense. So the current state is reachable from the starting state. So phi is true from that starting state. So we know that we can get there. It can't become false because we can't reverse it. And since it was true earlier, it's stable, we know that it's still true. We know that we went through that path. So I'm going to generalize this now and say, remember when I was talking about those consistent states? Well, if you go through a consistent state, you know what's in the database, and you know that it's not going to become inconsistent. So you know that you were consistent at one point. This is why we reboot. I mean, in essence, this is the reason you reboot. Rebooting goes back to a known consistent state. It goes back to some stable state. Now, we are wandering from one stable state to another stable state. The question is going to be, how do we get there? And the reason we want to know how we get there is because, remember, what I said was we have to be able to recover from failure, and failure is going to be defined as getting from an inconsistent state, somewhere along the path from one consistent state to another consistent state. We're here. How do we get back there or up there? Because we're walking lots of sub-pieces. We have lots of little inconsistent states that we don't want to expose to the rest of the world, but we have to actually make them. We have to make these changes one at a time. We're breaking the multi-tier B+ tree into pieces. We have to do that. How do we make sure that the only thing that anyone outside of us sees is the consistent state? That's the same thing we did with locking. Locking is a really simple example of this property. I guarantee consistency by grabbing the lock, changing, so I do a read, modify, write cycle to the value, and then I release the lock. So no one else sees those intermediate inconsistent states. While I'm holding the lock, I'm actually allowed to put it into inconsistent states, but I'm also responsible then for fixing it if things go wrong. So in other words, when I grab the lock and I make the internal value inconsistent, the protected region inconsistent, I have to guarantee that when I release the lock, it's consistent again. If I don't do that properly, I have a bug. This is what we're going to generalize into distributed systems. So the point here is, I don't care what the paths were through your code between grabbing the lock and releasing the lock, or between consistent state n and consistent state n plus 1. What I care about is that I know that we go from consistent state to consistent state. And that's why consistent but not actual is good enough for our reasoning purposes. If there's any path through there that doesn't go from consistent state to consistent state, then we have a bug. So when we start looking at the failures and we say, why did this fail? Because what does failure mean now? Sorry? It's inconsistent, right. So in other words, if I started modifying the B plus trees and halfway through I just said, sorry, I'm done, what's going to happen to the next component that comes along and tries to walk those B plus trees? Not going to work right. I mean, you have changed things around, and I don't know what you did, and I don't know how you did it, and I don't know what you were trying to do. So I'm left here scratching my head going, what shall I do? I don't know. I'll just crash. And that's what ends up happening. Now, maybe the inconsistent state is because the process that did it crashed. That's perfectly acceptable. It's still a bug. But this is just a different way of thinking about those kinds of bugs. Excellent answer, by the way. Absolutely right. We need to think about those kinds of bugs. That's why I keep talking about looking at the failures and trying to figure out what we need to recover from the failure. Because in essence, saying the failure, how do we recover from it, is a different way of saying, how do I get back to a consistent state? And that's a lot of what we're going to keep doing over and over again in different ways. How many of you have ever heard of Bitcoin? I see 3 hands. Okay, great. So for the rest of you, Bitcoin is a digital currency that is built on top of something called a blockchain, which we'll talk about later in the class. And in a blockchain, we assume that there are bad people. Well, people's projecting a little bit much. There are bad entities in the world who are either broken or malicious. And so no one trusts anyone else. How do you build a system, a completely distributed system in which you're trading something of value, in this case a cryptocurrency, and guaranteeing that no one is falsifying it? Does anyone of the 3 hands who went up, do you know how Bitcoin actually provides evidence that you aren't falsifying your work?
Multiple copies of the same transaction so that you can tally it with people.
Yeah, but you're missing the point that actually shows that you did something with it.
Certification, authorization, or something?
It's called proof of work. Does anybody know how Bitcoin implements proof of work?
Very roughly. I think you try to find some kind of data that will make the hash start with zeros.
That's actually pretty close to the way it works. Okay, so there's this thing. So I'm hearing the pieces here. That's what's kind of fun about this. Is like people vaguely go, I don't know, it's some sort of scam thing that people use for doing, shady transactions over the internet, and they do. It uses, I think the best mental model I have for this is that it uses double entry bookkeeping. So it's a ledger of data. The first thing in the ledger is, in fact, the hash value of the previous ledger page. So we start with the hash value of the previous ledger page, and then we put transactions. And now this is like double entry bookkeeping, where all of the things in the left column and the right column have to add up to the same value at the bottom. Those are the transactions that we insert into this ledger. And the inflow, the Bitcoins that people are putting into this ledger, and the outflows, the Bitcoins that are going outside this ledger, all have to be perfectly balanced. Plus, when you, as a reward for actually doing this work, you get to add the creation of new Bitcoins. Then there is what's called a nonce. This is a magical number that you get to find that says when you run a SHA-256 checksum over everything on this page, including the nonce, the hash value that comes back has a certain number of leading zeros. Now that certain number is in fact actually negotiated by the network. It's called the difficulty. And how do you do that? Anybody know anything about SHA-256? It is a cryptographic hash function. And what that actually means is you can't figure out from the hash value what the data was. But it's cheap to compute for a single ledger page, but trying to figure out the magic nonce that you can put there, and there's infinitely many of, well, finitely many because it's a finite field, but there's a large number of them, that will cause the hash value to have lots of leading zeros, turns out to be hard to solve. And so the way they approach this is they do it with brute force. You literally just guess. So I'm participating in the Bitcoin revolution. I'm going to guess. I'm going to start with 0, then I'm going to try 1, then I'm going to try 2. And the beautiful part about this, it can actually be sharded. So you decide you're going to work with me. So I'll do 0, 2, 4, 6. You'll do 1, 3, 5, 7. There you go. And we can keep doing this as we add more people to our collective. And eventually, one of us discovers a number, the nonce, that we can put in there that will give us a hash value that satisfies the complexity requirement, which is the number of leading zeros. And we then take that block, which is all signed, because it's tied into the previous block. This is what actually makes it really hard. All signed, and we flood it out to the network. And everybody else can look at it, and it's very cheap for them to validate that the checksum is correct. It's hard to generate that checksum to meet the difficulty requirement. It's very easy to check it. So everybody else looks at it, they say, yeah, you're right, and then they add that ledger to their database. And that is, in a nutshell, what all blockchain protocols are. It's really simple. It's not nearly as complicated. You need to read these things and like people get off on weird tangents, and then you're like, wait a minute, this is double entry bookkeeping with a little bit of computer science mixed in. This isn't high tech, it's low tech. Even the brute force part is low tech. The reason this works is because it is actually possible for people to forge the pages, to split the history. But it's actually very difficult to do. And because these chain together, the farther back the page is, the more computationally expensive it becomes to try and change the history. So the window for Bitcoin, practically speaking, is under 60 minutes. There's one new ledger page per 10-minute interval. So after about an hour, all transactions that are more than that age are in fact stable. But there is this window where, in theory, someone could disagree. You could have two different nodes that present a potential solution at the same time. And the network will choose them. And it pretty much chooses them based upon propagation delay. So whoever gets the message first tends to win. Now, there are interesting ramifications to this, but I'll leave it at that. I think it's actually a nice example of stable, and it's distributed systems-y, and it demystifies something that maybe you were like kind of surprised about. How many of you own Bitcoin? Do you own one Bitcoin? No. I have owned more than one Bitcoin in the past, but I mean, I looked at it and I said, this doesn't make any sense to me, so I sold it at, like $10,000 or something. I bought it at 130. So I have a friend who paid his way through university, undergraduate university, by using the computers in the computer lab to generate Bitcoin. So that was a long time ago. It was more than a decade ago now at this point. It was pretty funny. And then even I haven't talked to him recently, but at one point he was making enough money trading cryptocurrencies that he paid off his house and had, was putting money away for retirement and paying lots of taxes because of it. And he was having a lot of fun. It's not a great way to get rich these days, though.
Wait, so if you have more participants in the blockchain, does it become faster to find the nodes?
And that's actually why they have to increase the difficulty. So the answer is yes. So the way that they deal with more compute power is they increase the difficulty of the acceptable hashes. That's why that's an important value. Now, when I have you signing, I know it's annoying, I have you signing your commits, I'm trying to do essentially the same kind of thing, which is what you're doing is creating proof of work. It's a cheap proof of work for you because you're just simply saying, hey, I did this. Then you can submit something to Canvas by just simply giving me a hash. That hash now becomes difficult to alter. You can't go back and change the history very easily. You can if you really work at it, because Git is only using an MD5 hash, which is actually slightly forgeable. Slightly forgeable. You only need about $40,000 worth of, well, last time Google did it, I think it was like about $40,000 worth of compute time to hedge it. You were going to.
Yeah. You say that they're going to increase the difficulty of the hash? Like who's the
It's actually part of the decision protocol. So there's a management protocol. You can go look at the Bitcoin code. It's actually all public. You can actually see how they negotiate it. I haven't personally gone and looked at that. I just know that they negotiate it based upon the amount of hashing that is available on the network. And the goal that they use is to make the time to solve the next block about 10 minutes. So when you start seeing blocks getting solved faster than that, like maybe it creeps down to 6 or 7 minutes, then what will happen is that people will vote to increase the difficulty. And if it starts going up to like 12 or 14 minutes, then they would vote to decrease. I don't know if they've decreased it or not. I haven't spent that much time looking at it. But that is part of the protocol itself, the management level protocol. Is there a question? I thought I saw a hand, but I'm old. I imagine things. So what are the limitations here? Again, Chandry-Lamport gave us this interesting situation where the FIFO channels, well, they are FIFO channels. What happens if we reorder them? I already mentioned this possibility. What happens if messages are lost, and what happens if the network partitions? The basic finding of Chandry-Lamport is nice and crisp and easy to understand. When we start adding these additional assumptions in here, that's when things get messy and more complicated, and we can't guarantee as much. So one way to think of those markers is that they are a form of logical timestamp. Essentially, if you think about what we just did, was we described a vector clock, or maybe a matrix clock. The practical applications of this include checkpointing, fault-tolerant systems that save consistent snapshots. It's very common. I mean, it's not radically different than what we're doing in the first design project, which I moved because I'm going to be talking about two-phase commit, and I wanted to do that before you started that project rather than when you were just finishing it. So the design project 1 actually shifted by 1 week. So you don't have anything that you're starting today on that. You'll start it next Tuesday. And of course, that knocked everything else after it by a week. So in debugging, we can use this kind of technique of grabbing these snapshots as a way of recording global state. Again, because it doesn't actually guarantee that we went through the state that we're capturing, it doesn't always give us the information that says this is what the bug is, but it gives us something better than having no state at all. You can add termination detection. There's something called Dijkstra-Scholten, which allows you to look using a weighting scheme for processes that have terminated. It turns out that dead node detectors are notoriously difficult to build. And there's a whole area of work around how do you detect when a node has failed versus when it's partitioned from the network. I mean, aren't those indistinguishable in a message-oriented system? How do I know you're alive? How do you know you're alive? I mean, but that's a different question, metaphysical. I mean, I don't know. When I'm trying to reach a website and it says it's dead, I just assume that it's because it's dead, not because the network is partitioned. But I don't really know. In distributed reference counting, you can actually build garbage collectors, believe it or not. You can actually keep track of how many references are there outstanding to something. Very interesting. This idea that we're talking about where we have consistent, eventually consistent, causally consistent, all these different consistency models that don't necessarily mean consistent right now. They mean consistent at some points. And we are going to reason around those consistency points and kind of look at the mush in the middle and go, that's where all the hard parts are. And that's the reason that we're talking about all of this stuff, because dealing with the hard part, it's not the consistent states. Those are easy. Those are really easy. You know, you just reboot, you go back there. It's the inconsistent states, which is we've changed, and this is why databases are so important. We've changed something on disk that's made it inconsistent. How do I recover from that? The database people actually have a solution for that. And we will get to that because I'm going to talk about that as we start talking about recovery from failure. So beyond these snapshots, we actually have lattice theory. And I'm not going to go into a lot of detail about lattice theory. It's actually very interesting. It gives us what are called CRDTs, consistent, oh my gosh. I don't even remember the name of the meaning of the acronym off the top of my head now. CRDTs are a form of data structure that are implemented using lattice theory as the driver by a group at Berkeley. They did this research. Hellerstein did this research 13 years ago, 14 years ago, something like that. And they are used extensively for building eventually consistent systems. Now, eventually consistent systems are great because they allow for us to keep making forward progress even if we're using old data. A lot of message passing systems actually are eventually consistent. Have you ever seen a situation where you've been writing messages back and forth to somebody and their messages then appear before the one you sent, even though you sent it after, and you're like, what? So you didn't see their message, you saw some previous state. That's an eventually consistent system. What it did was it said, oh, well, this one actually should have been here. Not all messaging apps work that way, but some of them do. There we go. Conflict-free replicated data types. See, my memory is bad enough. I put it on the slide and didn't notice it down here. It was on the previous one. Okay. Version vectors in distributed databases. One of the solutions to the I have to split n things in the B tree is that I keep multiple versions of the B tree. And I pick the version that is consistent. So, version n plus 1 isn't consistent yet because it's not all represented in all the version vectors I'm looking at. So I will use the version vector that is consistent. And that will give me a mechanism of dealing with a variety of failures. And then we're going to talk about causal consistency models, where causal consistency is this A before B model. And that's really what lattices end up doing, right? Is that lattices say this came before this, but it doesn't really say about what the ordering was of all the things in between. Because I could through this route, or through that route, or through this other route, or maybe I did go through this really strange route, loops around a couple of times and then comes back down. Those things all happen. They're all legit. Causal consistency provides us with the tools necessary to reason about these sorts of complex structures and to use them. Even if we don't necessarily always look at them and go, oh, well, this is really obvious. It's not obvious. It actually does get complicated. And it's not like lattice theories are something that you're going to get out of a 75-minute lecture. Lattice theory is something that you're going to read that there are books about, whole books. And these are dense mathematics textbook kind of books and papers and whatnot. How many of you like reading dense mathematical books and papers? There's got to be somebody who likes it. This is actually where you can use LLMs quite effectively. They're trained on that stuff. Sorry?
Sometimes if it's weird, like weird enough.
Oh yeah. I mean, everything in this field is weird. Some of the people are weird too, but I'm not saying about anything about anyone in here except maybe the instructor who's a little dodgy. So, to summarize what we've been talking about, Chandry-Lamport, we're using these markers to compute consistent snapshots. The snapshot is consistent but doesn't necessarily correspond to what actually happened. Reachability is the idea that there was a path that could have gone through this way. We have stable properties, so if it was true in the snapshot, it's true now. Stability is actually really important, especially for things like databases, where once I write something on the disk, of course I assume that when I read it back, it's going to be what I wrote. And when that breaks, the database breaks. Lattice structures are really kind of interesting. We're going to use these things as we begin to build on our understanding of consistency and replication and consensus. So if you didn't already look at Chandry-Lamport and Mattern, they're good to look at. The paper should be linked on Canvas. If they're not, slap me because I meant them to be linked. Let's see, self-assessment opens in 20 minutes. The self-assessment, so the last self-assessment, there were still 13 of those hideous questions at the beginning. I actually used all of the answers to the first 3 of those, believe it or not. I had to spend a bit of time, but it was actually really interesting because it was nice to see that people were understanding causality better after the 3rd lecture. And that was really nice that it showed up there. I used the same quizzes as I did the last time in this class, and I think this was the point that I realized, and this was 2.5 years ago, and I realized that 13 questions at the beginning is a little bit much. I know somebody commented on that, you're absolutely right. Now what it'll do is it'll be sampling 2 out of the 13 going forward. And I can't fix the 13 for that was due today, but I'll see if I can remember this 2.5 years from now when I try to use them again. It still was interesting, and a lot of people didn't answer. That was great. It actually forced me to also do something else, which was, and I was talking about this a little bit today, this idea that there are 3 possible answers, yes, no, maybe. It's very easy for us to say what we want is yes or no, but often the reality is that the world is made up of lots of maybes, or I'm not sures, or I'm uncertain. And there are actually branches, esoteric branches of mathematics that I'm actually having a lot of fun with that say, if the world's not Boolean, if it's not true or false, what could it be? And the observation is the world could actually be some combination of true, false, or indeterminate. In other words, I don't know, or we don't have a clear answer. And it's been really interesting because my research lately has been about epistemic honesty in predictive token models. Basically, large language models are the most common example of that. I don't know, have any of you ever used a large language model? ChatGPT? Ever asked it a question and gotten back something you looked at and said, this is lie, or this is wrong? So the question that I asked was, why does it do that? And there's a complex set of answers as to why it does that. Not the least of which is when they first train the models, they're trained on coherence. So they pour all of the text of the universe into them, well, at least our little piece of the universe into them, and then they teach them to give back coherent continuations, responses. But coherence doesn't necessarily mean true. And the true part is sort of baked in after the fact, but it's also baked in along with some interesting data around what people like to hear. And what people like to hear are strongly worded responses that sound authoritative. Does that make them true? Have you ever heard someone insist that they are absolutely correct, and you know they're wrong? Like me, I do it all the time, right? And so I've been looking at, can you actually detect that this is happening? And it turns out you can. The data is actually there in the models themselves. So the large language model is no more cognizant of how it thinks than you are about how you think. You start thinking about something, you don't have a map in front of you that says, these are the parts of my brain that are lighting up. We can put you in brain scanners, and people do that. We can put you in a brain scanner. We can see what lights up when you do different things. And we can do that with large language models as well, with these predictive models. And it's really kind of cool, because when it starts making stuff up, you actually can see patterns in the metadata of the model itself, but that metadata all gets thrown away at the boundary, because the only thing that gets returned is the answer. Now, that's the way that humans already operate, so I think that we're pretty comfortable with that. Nobody stepped back and said, hey, could we get a brain scan with every one of these, please? Now, maybe you don't want the full brain scan. It turns out that the brain scan size, the data in the brain scan, is larger than the response. So what I've been looking at lately is, can you compress that down to something that isn't a single scalar value, lying, not lying, but rather something that's much more nuanced than that? Currently what I'm working on, I don't know if you've ever seen one of those truth or falsity meters like on a news article. I'm like, that's what I want. I want a little gauge that says, the model thinks it's lying. The model thinks it's being true. Now, just because the model thinks that it's being truthful doesn't mean it's true either. You train models on the data that's available. Some of the data that's available will be wrong. And of course, we know that doesn't happen to humans at all. So that's been interesting. So it keeps teaching me that one of the things that's important is not to collapse down into certainty too early. Premature collapse. That's why when you start, I was mentioning before, if you ask them to tell you, they give you an answer, they propose an answer to you, you come back to them and you say, show me the non-inferior alternatives to the answer or answers that you have suggested. ChatGPT is really good now. It gives you continuation things, right? Would you like, and then it gives you 3 things. And I love to go back and say, what things should you have suggested that you didn't suggest? Take the whole list of all these things and then do a pro and con analysis, strength and weakness analysis of each of those, and then recommend one to me. It's so much fun. It's actually really interesting. I mean, they have a lot of interesting ability that gets squished into the Family Feud model of just returning a selective answer. But it ties into this because this is the same kind of indeterminacy. Many times we don't actually know what's going on, and we're not entirely sure. So I'll stop there. Thanks very much for listening, and I will see you again next Thursday, day after tomorrow.